Okay, so last week we focused on calculating length, right, with perimeter and area, and today the focus will be on angles. We divide the lesson into three parts. The first one with triangles, the second part we will deal with circles, and the last one. So in the first two parts, we review basic theorems and tools that will help us solve most problems in Math Kangaroo competitions. Some of them require a little bit more advanced techniques that we will talk about in part three. So for triangles, the most basic theorem is sum of angles in a triangle is 180 degrees. And if you have a polygon, you just divide it into smaller triangles, right, and sum up the angles. Then this theorem is very straightforward, but super useful. If you have a triangle here, then the exterior angle at C is equal to the sum of the interior angles at A and B, right? Because C, the exterior angle here is supplementary to the interior angle at C, and angle C plus alpha plus beta is 180 degrees, so gamma must be equal to alpha plus beta. Very straightforward, but super useful. And then the next step when we deal with triangle is that always identify all the special triangles that you can see in the problems. And that means the isosceles triangles where the bisectors is also the median and also the altitude. Right triangles, equilateral triangles, and of course the 90, 60, 30 degree triangles in which you have the median here equal to half of hypotenuse, and this triangle MEC is equilateral. And of course the right isosceles triangles, right? So when you see them, just mark all the lengths, all the angles in the figures. And the next step when we have to deal with angle is that you actually have to prove pairs of congruent or similar triangles. So for congruent triangles, most of the time we will use a side-side-side test or the side angle side test to prove that the two triangles are congruent. And when they are congruent right away, we have three pairs of equal angles, right? And similarly, for similar triangles, then we usually use the side-side-side or the side angle side theorems to prove that they are similar. And again, we have three pairs of equal angles. Yes, so I think that's pretty much what we need to use to solve maybe 80-90% of problems that involve triangles or polygons. So let's get started. Square ABCD and equilateral triangle DCE are on a plane. See the picture here. What is the measure angle AEB? And remember to mark all the equal lengths and angles that you see on the pictures. That will help you allow you to see things that are not obvious. So ABC is a square and DC is equilateral. If you have the handouts, that's great. If not, then try to, draw. And when you draw as accurately as you can, draw to scale. Right? So I mark all the lengths is equilaterals. This is squares. So I have a bunch of lengths that are congruent. And then I also want to mark, if you want to, all the angles. And this one, because it's equilateral, so this one is 60 degrees. And here also 60 degrees. Yes. So after we mark that, we know that ECB is isosceles, right? Because EC equal to CB. And that means this angle alpha here and alpha here is the same. And same on the other side, also alpha is due to symmetry. And this angle here is 60 plus 90, that's 150, right? 150 degrees. So that means each of these going to be equal to 15 degrees, so that they make up into 180. And so have a 15 here, have a 15 here, and DEC is 60 degrees. So the angles that we are looking for is 30 degrees. And a lot of time for this question, you can just, just mark and everything on the pictures without having to write anything. So that's 30. Okay, that's the first step of problems when we just have to identify special triangles. Great that you all got the correct answer. So now go to question number 2. No, a little bit. I will have a, let M be the point where all the altitudes of the acute triangle ABC meet. If AB is equal to CM, what is the measure of the angle at vertex C of triangle ABC? So basically we are asked to calculate, this angle, right? And let me mark, this one is not, I really recommend you study geometry, draw to scale, because that a lot of times it's have you see the answer right away. But in this case, I probably just highlight using different colors. So CM is equal to AB, right? You want to, so these two lengths, it'll be ideal if they are drawn to scale, but if not, then mark them, color them. And thanks, David, for marking here the altitude. So these are also, okay, this is not so good. Yeah, these are perpendicular. These are 90 degrees, and these are just super helpful. Mm. So remember the first step, you use the sum of angles in the triangle 180 degrees. The second step is identify all the special triangles as much as you can. And the third step is that have to find pairs of either congruent or similar triangles. There's a lot going on, but it's kind of methodological. That's all the tools that I have. I maybe just leave this one got confusing. Yeah, thank you, David. You can also do congruent as well, because yeah, I think similar and that one side the same, so it becomes congruent. Oh, we got the first answer. Okay. So for congruent, we use the first, usually we use a side or side angle side for congruent triangle. And we mark as many. So let's, okay, good. So you already put in the answer, so we can get started. Let's see, we have this angle here, right? Because I see the equal lengths. Somehow I want to make use of this information. The two lengths are equal. And how do I do that? These are CMA and A prime B, they are right triangle, and these are hypotenuses, right? So maybe I can sort of work backward. Maybe I can try to prove that they are congruent. And how do I do that? This angle equal to this angle, right? Because they are vertical. So that means, and this angle M is complementary to angle alpha here, and this one is complementary to angle beta over here. So actually, these are also alpha. Do you see that? So that means an alpha here. That means this one is beta, and that one is also beta because they are complementary. So now we have a triangle C. We have a CMA prime. It is actually congruent to A prime B, right? Because we have the side angle theorem. And from that, right away, you can get that C A prime equals to A prime. Right? It's not very pleasing to look at the picture because not to scale, but this is longer than that. So CA prime is equal to AA prime. That means the triangle CA prime A is right and isosceles, right? And that means the answer is at C, 45 degrees. Yes. 45 degrees. And I said, if you draw it to scale, you would see right away that A prime C is right isosceles, and then you go back what you try to prove that. Good. Next, this one, David, could you please do this question?
Okay, question 3. Which side of the polygon shown in the picture is the shortest? Yeah, very small problem statement, a lot of segments. So the question really becomes, how do we compare the length of the segments when we're not given any lengths, right? We need some other trick. And so once we figure that out, which is, not hard at all, once we think of the way to compare angles, to compare sides, not angles, then the trick is just to just keep comparing everything and list it. So this is another angle chasing problem, except it's a side chasing problem, right? Again, how do you solve it? Just keep getting stuff until you find what you want.
Oh, do you want to show the side rules or?
Um, I guess I could show exactly, but there's
I
no
have it.
reason to get into things like law of sines, right?
Okay. Okay.
The main trick is to realize, yeah, the bigger the angle, the bigger the side is.
Yes, because it's anchor. Okay. So I have the next slide I can show, and then we come back to this if you want. I mean, we may not need this, but yes. So if you draw a triangle, then you see that the bigger the length, right? Then the bigger the angle. So if you need to review, that is a slide you can review. And then we go back to our question here.
All right, we have our first answer, which is some pretty quick bashing. I'm just going to start bashing slowly as we get through this, because that's what this problem is. We bash, okay? So first of all, let's start with the first triangle. Maybe you started from the other side. That's fine too. It really doesn't matter. I'm going to start with triangle EDM. First of all, if the sum of these angles is 180 degrees, that means that this angle here is also 42 degrees, because 42 plus 42 plus 96 equals 180. That's just doable arithmetic, right? That means that this is an isosceles triangle. These two sides are equal, and EM is clearly larger. EM is bigger because the opposite angle here is very big. And by the law of sines, that means that EM is also very big. So that tells us that whatever the smallest thing is, it's not EM, right? In the next triangle, what do we see? Well, this angle over here is 59 degrees, right? Has to be 59 degrees because, no, 58 degrees, sorry. It's 58 degrees because 58 plus 61 plus 61 is 180, right? We're just using the sum of the angles as 180 theorem. And since 58 is smaller than 61, by the way, this is equal and this is equal too because a bunch of isosceles triangles. That means that DC is smaller than either DM or MC because the opposite angle is smaller. So that means that the smallest thing is definitely not this, right? We can get rid of these two. They're too big. Now 45, 45, what's the other angle? What triangle has 45, 45? Obviously 45, 45, 90 triangles. That means that BC is even bigger than CM, right? This is a hypotenuse. The hypotenuse is always bigger in a right triangle. So this isn't the smallest either. Then, because we know that MB is too big, just because we know MB is bigger than DC, since DM is, and these are all equal, MB is the smallest side in this final triangle AMB because it has the smallest angle opposite to it. 35 degrees is greater, so AM is bigger. And then the angle that's left here is over 100 degrees, something very big. So whatever it is, we know that AB is also huge, which tells us that the only thing we're left with is DC. And that would be our answer. That's the smallest one. And so the only thing we did is we basically did angle chasing and found the smallest angles and used that to find the small sides because we have this relationship by the famously abbreviated law of sines. This is how it's typically written.
Yeah, thank you. Thank you, David. Okay, good. So let's move to the next part with circles. For circle, I think we briefly talked about circle last time, about tangential circle. So there's another thing we want to review in the circles. All inscribable angles subtended by the same arc are equal, and that also equal to half of the center circle subtended by the same arc. I think that's how they talk about designing a theater, right? If the screen is here and everyone sit here, then they would have the same angle to the screen. This is the center of the circle. And then because the half a circle is 180 degrees, so an inscribable angle subtended by a semicircle when AB here's diameter is 90 degrees. So anytime you see a diameter here, you want to mark that angle is equal to 90 degrees. So that is super helpful. And lastly, for the tangential line to a circle, if AB is tangent to the circle O and the point is P, then the radius OP is perpendicular to AB, and that is something you also want to mark on the pictures as soon as you see it. So I think combined with what we had with triangle and with circles, let's do a few questions here. So the first two questions are just pretty much basic review of inscribed angles. Let's see if we can get it. What is the measure of angle 5 shown in the pictures? So you may want to label it A, B, C, D. So ABD is 30. This angle here looking at this arc. And phi is angle looking at the arc BC. This is not the center, it's just maybe we put it P where AD intersect with BC. So similar to length, we have a picture with angles. Let's try to mark as many angles as you can find in the pictures.
Again, angle chasing. There's
Yes.
only less than 10 angles in this entire thing, no matter how hard you try. That means you can brute force, which
Yes.
is brute force is very useful in angle problems because at some point there's no trick. It's just you have a bunch of angles, some of them are equal. You can find some by doing the subtractions in a triangle. Just pummel it down, and eventually you'll have no angles left, and you'll find them.
Yes. Yeah. So this 70, not super useful. It's it's not the center of the circles right here. We look at 30 first, right? Because 30 is the inscriber angle looking at this arc AD. And then we have another angle also subtended by arc AD, which is this one. So I can right away mark that this one equal to 30 degrees. Yeah, I think you figured out. Oh, 30 degrees. And then now we look at this triangle PCD over here, right? We talk about the exterior angle theorem. And this is a classical case. We have an exterior angle 70 degrees here at P and an interior angle at C equal 30 degrees. So right away, we can have phi, and phi must be equal to 40 degrees, right? Of course, I mean, you can also go 70 degrees, and this one is 110, and then subtract it, but just really bypass this pass. We just learn to bypass this pass. It's gonna speed up the calculation and help us see things much quicker. Okay, so 40 degrees. Yeah, I can't understand why you got. Oh, maybe some got 7. Oh, some got 30 degrees, 35, which is half of 70, because maybe you think that 70 here is the center. Remember,
But everyone actually said,
yeah, right? Because remember in this one, this point here must be the center. That's why it's called the center angle, because this must be the center of the circle, and in this case, it's not. Okay, good. So it's good that we review that theorem. Okay, next one. In the figure, you see points A, B, C, D, and on a circle, this on a circle. Chord AB is the diameter of this circle, and the measure of angle ABC is 35 degrees. What is the measure of angle BDC? Right. So right away, when you see that chord AB is diameter, what do you do? So just quickly draw the pictures and draw AB as a diameter. You want to do that. I may even mark O here. You don't have to, draw much. So just mark O here so that you know that AB goes through the center of the circle. I see. Oh, okay, good. Good. I think some of you realized it. So AB here, as we said earlier, yes, we want to draw that. We want to draw this line because ADB is circle. So right away, ACB has to be 90 degrees. So our old trick, right? 35 degrees here, 90 here. That means this one's going to be 55, and I just mark it. 55 degrees, and this is on a circle, so I know I have to invoke the inscriber circle. triangle angle theorem, and all of you got it. 55 subtended by this arc CB, that means the same thing here, also equal to 55 degrees, right? So this step, one of the most beautiful theorems in circles, but you should do a few examples and, get a hang of that and be confident using it. Okay, good. So I hope we reviewed the basic, and now we got to something a little bit more complex. So, David, yeah, could you do this question, please?
Okay, here we go. Right. A fear. Okay, anyway, no. In the picture, PT is tangent to circle C with center O, and PS bisects angle TPR. Calculate the measure of angle TSB. So we're going to apply everything we've done with angles so far, both with circles and both things without circles. And we're going to start by doing what? Chasing, angle chase. Draw your lines, chase your angles, try to find that extra thing, and hopefully, eventually the angle that we want will just fall into your lap.
Yes, so thank for labeling, that means PS, bisect, and then PT is tangent to C, right? So we want to represent that information on the picture. So how do we do that? Yeah, wait time so we can figure this one out.
Okay, so probably the reason that this is hard, really, is because we don't really have enough on this diagram. And this
Yeah.
is a very common strategy. It's just draw the extra line. Draw the line that looks nice, the line that matters. Often it's an altitude. We will see one of those later. Often it's a radius. And in this case, we have a circle, which means it seems very logical that one should go ahead and try and draw this and see what that's a terrible line. Let me actually undo that. That's too bad. Line.
You can draw straight.
Yeah, there you go. Perfect.
Okay, good.
So we should draw this radius, which, as we know very well, is equal to this radius, and just see what we can conclude from it, right? Suddenly, just drawing that line, and that's why it's important, it brings up a whole host of new opportunities, right? For one thing, we know that whatever this angle is, beta, let's say, this angle is the same because, look, isosceles triangle. We also know that we have a radius and a tangent, which means that this over here, I don't have enough colors, is a 90-degree angle. And at this point, we can start chasing a bit more. So I'll give a bit more time before I go to the next step, before I do some more chasing. And this is the angle we're looking for, obviously. And if this is helpful, Okay, good. We got one. Let's start going slowly. So this is just a little hint I gave at the end of the problem, which tells us that TSP is just alpha plus beta because it's an exterior angle to the triangle. Welcome now. That's quite a while to show up. So this exterior angle thing is very useful because we can use the fact that beta plus beta also sums up to this angle here, which tells us that 2 alpha plus 2 beta, these two angles, plus 90 degrees equals 180, right? They make a triangle, which means that 2 times alpha plus beta, I'm going to write this, 2 alpha plus 2 beta equals 90 degrees. They're complementary. They're in a right triangle, which means that alpha plus beta equals half of that, right? Or 45 degrees. And suddenly we're done, believe it or not, because once we have that, we know that TSP is just the sum of alpha and beta being an exterior angle, which we know is 45, which would give us an answer of B. So the trick here was draw the extra line. That was the new strategy, really. We didn't have that, and we needed that line. But then once we got there, we just were chasing angles, right? I chased this angle, I chased this angle, I chased alpha, beta. In principle, I could have just gotten all the angles in this entire thing. I knew which ones were necessary because I've done this problem, right? I know what angles I needed to pick, so I only showed you the necessary ones. But if you solve this problem by getting more angles than you needed and then eventually finding the right one, that's okay too, right? As long as eventually we brute force our way to it and we have few enough angles that we can do it in the few minutes we have in Math Kangaroo, that's really all that matters. So if your solution wasn't as efficient, don't feel bad because I had prior experience. I knew what to look for, right?
Yeah,
So
thank you, David. Yes, a very useful tip. So, there's a lot of angles, a lot of notation. So we just decided to, put the things here. You can review, pause the video, and review at home if you need to. Sort of nice and neat typing up of what David just presented. Okay, so we finished with part A with triangles, polygons, part C with circles, and I would say most of the time, maybe 80–90% of the time, that would be up for you to solve Math Kangaroo geometries, but maybe 5%, 10% of the questions that require you to do a little bit more work. So that more work is to draw the actual lines in this case. So the previous line that we draw over here, we actually, can get from the question because we know that PT is a tangential to OT. And sometimes we have to draw, actualize out of nowhere. We just have to invent that. And then we have to use, if you have advanced theorems, sometimes you can have advantage, but I don't know. I don't think like Math Kangaroo really test how far you know ahead of time. So I would not worry too much about advanced theorems like calculating the area of triangle, knowing its length, something like that. It should not worry too much about that. And if you study trigonometry, yes, sometimes you can, have advantage. You know that, but we're going to show that you can use elementary Euclidean geometry to solve most, questions. And
trigonometry can be a shortcut. That's really what it
yeah,
is. And I've done problems where it would take, 4 or 5 minutes if you did it Euclidean, drawing a bunch of weird extra lines and trying things.
yeah.
But then if you know the trig, it's not that you need it. It's just that if you have it, sometimes they can just go like that. And it's a useful thing to have.
That's true. Yeah. So in the next few sort of more challenging questions, we will present several solutions. And then for Euclidean geometry, always draw as accurate as you can. Yeah, I love construction questions when you have to choose a compass and a straight edge. So I don't think this one is probably the most basic trigonometry rules. Some of the questions required. I would not worry too much. But I just put it here for completeness. Okay, so let's go for this question. 3 squares form a rectangle. See the picture here, right? All 3 squares. Lines AE intersect with CH at point P. What is the measure of angle CPE? This one. So we have time. So we give you some quiet time, maybe 2 minutes for you to Think about it. And you know that if you have a compass and a triangle or a ruler or straight edge where you draw it accurately, and you can actually measure this one. Got it. Not a good thing, but once you lots of time when you know the answer, it helps you to sort of construct the solutions. And as we said earlier, if you know trigonometry, use it, but we don't need it. We can use it in elementary way. Okay, so 2.5 minutes past. So let's start it in the first step. This angle P here, just in the middle of figure, right? Doesn't look very nice. So maybe I want to break it down into, other angles that might be easier to calculate. So just use the exterior angle theorem here. We know that this angle P here equal to alpha and beta. That would be the first step. And alpha beta are so much nicer than P, right? Because alpha is an angle of this AED, this right triangle, and we know ED is 1, AD is 3. And similarly, beta is an angle in this AHC triangle with length 1 and 2. So it looks like alpha and beta are more manageable than P. That would be the first step. And from here, let's see if we can find out what's alpha plus beta. Wow, great. Okay, we got the answer, so we can get started. Alpha and beta, they are separate. I need to add them up, right? So naturally, I want to bring them together. There are many different ways to do that, but I would like to bring beta next to alpha. And one way to do that, if I extend this FC to equal the length of the side length of the square, then, for example, I go this point M, then I connect A and M. Then right away, I know that AM is parallel to HC, right? So this angle is beta. Or you can see that the HAC and MCA, they are congruent. So now I know that alpha and beta, they're next to each other, right? So I calculate the angle EAM? Hey, it's a lot to type, so I just move to the next slide, sort of easier to explain here. So what we said earlier, I bring beta here next to alpha. So EAM is the angle that I'm I need to calculate, but I look at over here, there's a lot of squares that I haven't made use of, right? So let's connect E and M, A and M here, and let me make life easier by just call the length of the side length of each square is 1. So and I have a bunch of right triangles. So let's just use the Pythagorean theorem. So if I look at angle ACM, AM squared is going to be equal to 1 square plus 2 squares that equal to 5, right? I mean, that's AM squared, not just AM. And then similarly, if I look over here, FEM is a right triangle. So 1 square plus 2 square, ME square is going to be equal to 5 as well. And this is ME square, not ME. And finally, I look at this right triangle AHE. That means AE square is equal to 1 square plus 3 squares, that is 10, right? So AE square equal to 10. And that's the thing with geometry. The question gave us 3 right triangles, and we have to, and they are, put next to each other in this particular configuration. So I have to make use of all information. If I haven't made use of all information, I know that, I wouldn't be able to get to the solutions. So now it's nice to have a 5, and 5 plus 5 is 10. So again, using the Pythagorean theorem, I know that AME is actually an isosceles, right? Isosceles triangle. So alpha plus beta equal to 45 degrees. And for this one, part of the reason you can get to the solution very quickly is because the pictures are very much drawn to scale. So once you bring beta and alpha here, I think you can quickly see right away that AME is a right isosceles triangle, and we just sort of work backward to see how can I prove that.
There's already another completely separate solution we'll show, but there are a million ways to do geometry problems. And in particular, the way that I solved this, I got to this point, and what I realized is EFM is also a right triangle with this ratio 1 to 2,
Yes.
which means that this angle is also beta, right? It's
Yes.
beta because we have a congruent triangle to ACM, to ACH, they're all the same. And since this angle is 90 minus beta, because you've got a right angle here, that means that this entire angle is 90, which tells me immediately 90 degrees,
Oh.
these are the same, 45. So again, there's a billion ways, and this is just one solution of multiple.
Exactly. And that's like, I feel like sometimes we do with geometry. It's like you playing chess, you look at this direction, like that direction is always something interesting going on, and we just have to put things together. And then, as I said earlier, you can use trigonometry. Again, we have alpha and beta, and we know that tangent of alpha is 1/3, and tangent of beta is 1/2, right? AH over AC. And so if you know this formula, the thing with trigonometry is that you have to know it like by heart, you know it very well to be able to use it confidently. So that's why I don't think it makes sense for it to go with the theory. If you know it, you can do it. Most of the time, you can solve it without knowing it, but it's just so powerful. All the trigonometries are the ones that relate length and angles. So definitely that is something that you want to pursue.
And it is useful to know because those previous solutions did require ingenuity. You had to draw multiple new lines. You had to extend the figure out of the original because you have to literally think outside the box. You have a box of 3 squares. It really feels like the solution's supposed to be in that box, but no, you make it bigger. You draw all these lines outside of everything. And that's a very common theme in hard geometry problems, but it requires a lot of ingenuity and a lot of inspiration. And I guess the good thing about having trig is that if we don't have the time to think of that, or we just find ourselves not able to, we have the opportunity to just bash. And that's the only reason you'd want this. It's not as nice of a solution, it's not as elegant, but if you happen to know them by heart, then a
Yes,
lot less.
by all means, use them. And they are so powerful, we were able to do those things because angles is 945 degrees, but if like 42.5, then no, we need to use trigonometry. Okay, so another question that also has multiple solutions. I think it's a very beautiful questions. Let AD be the median of triangle ABC. If ACB is 30 degrees and ADB is 45, then what is measure of BAD? And of course, I want to label that BD is equal to DC. Always label everything in the pictures. So that was, okay, sorry, I just want to move it over here. So BD equal to DC. And then this one is 30 degrees, right? 30 degrees. This one is 45 degrees. And by now, I know that this one has to be 15, right? So I label as much as I can on the pictures and, now stop for a moment and see what can I do. So that's the typical question when we have, like two lengths that are equal. Not, and then we have to ask how to bring them together, how to make use of the information, because what I'm asked is not length. What I'm asking is angle, BAD, this angle. It's not the bisector, it's not the altitude, it is a median. We definitely need to draw actual lines, and which line is that? And definitely you can try, right? Just try. If it works, if it doesn't, we try something else. Yes, oh, good. That's interesting. Some student got it very quickly. Let's see, we can, yeah, too bad we don't know we don't know how the student solved it, but it's great that you got it so quickly. Okay, so let's go with, we have three different solutions. So let's get started, and you can also just send us the answer while we are discussing this. So to me, when I look this question, I have a 30 here and 15 here, and I just thought, okay, how I can make use of that information. I want to bring this length closer to this length, right, together. So one thing I can think of is that if I put M over here, such that maybe M and N, just any point over here, such that DM equals to DC, right? Then that serves two things. The first is that MDC is isosceles triangle, so I would have 30 degrees over here. And again, using the exterior angle theorems, I know this one equal to 15 degrees. And that means this AMD is also isosceles. So right away I have AM equal to MD. I have a bunch of equal lengths. And also MD is median of BMC, and it's also equal to half of BC. So that means this one is 90 degrees, right? So it looks like a good try. Tried a few things and I got this. Let's move to the next pictures whenever drawing is kind of more neat. Okay, so that's what we do over here. We have many different lengths that are equal to each other. And also we realize that this triangle BMC is 90, 30, 60 degrees. The BMD is equilateral, right? So that one is also equal to BD. So many equal lengths. And now right away, you see that AMB is a right isosceles triangle. This is 15 degrees, so this one is 30 degrees. Okay. So it looks like, oh, how do I draw this length? But it really just stems from the fact that I want to make use of the fact that these two are the same. And it's just draw and actualize that, make use of that information. And it's great because I think students figure it out. But when David looked at it, he had a different, he looked at it from a different angle, a different point of view. So he has a different solution. So David, please tell us how
This
to
is
solve it.
probably maybe not actually what you're thinking of because I do have to chase a lot more. I do have quite a bit of chasing to do. But what I saw when I did this problem was I was thinking, I have a bunch of angles that fit really well with right triangles, right? I have a 45-degree angle. I like right triangles with 45 degrees. I have a 30-degree angle. I love right triangles with 30 degrees. What I don't have is I don't have the right angle. So let me do that. I'm going to draw the altitudes. So I drew the altitude down to BC, which is also thinking outside the box, right? Because it's outside the triangle. And I drew the altitude H down to here. It's also important to know that this is 15 degrees. You can solve it in that same exterior angle way. What I really realized, though, is simply, if this is 45 degrees, this entire angle here has to be, this entire angle is 60 degrees because 30, 60, 90. And this smaller angle is 45 because 45, 45, 90, which is how I know this is a 15-degree angle. So that's step one. Immediately having two right triangles has given me this angle. I didn't use an exterior angle. I used the right triangles. The second thing I did, and this is a bit ugly, there's probably another solution which uses this diagram, which is neater, that will be shown. But I did a bunch of chasing with special triangles, right? I know this is 1. I know this whole thing is 2 because you have a 1, 2, root 3. No, really. Let's say AE is 1, right? It's just 1, because why not? Then I have a 1, root 3, 2 triangle because that's what 30, 60, 90 triangles are. We've looked at that. These are the side length ratios. I also know that this is root 2. I know that since these are the same, what did I even do? Okay, now I'm going to be, this is 1, so this whole thing is also 1, right? Which means that this is root 3 minus 1, right? So I'm just chasing sides here. It's really not that complicated, which tells me that this is root 3 minus 1 over 2. Root 3 minus 1 over 2, because you have half of this hypotenuse. This is 30, 60, 90 triangle, right? This is half of this because the angle of 30. Similarly, this has also got to be root 3 minus 1, which means that this is 1 minus root 3 minus 1, which is 2 minus root 3, this angle here. And what you realize is that if I do some more angle chasing just real quick, I'm almost done here. I know this is a bit messy, but every single step I'm doing makes sense, right? I just multiply by root 3. I multiply by 2. It looks like a lot, but every single line, I'm just plugging in the same rules. If it's 45, 45, 90, I have 1, 1, root 2. Otherwise, I have 1, root 3, and 2. 2 minus 3 minus root 3 over 2. And the reason that I do all this is because you realize something super important. The ratio of DH to AH is the same as the ratio of EB to AE. We did all that to realize that AEB is actually similar to AHD, which means that this angle is also 15 degrees, which means that since this angle is 45 degrees, the angle we're looking for is 30 degrees. So instead of angle chasing, I did line chasing. Every single step is simple, but there are a lot of them. But the reason I really wanted to show the solution is because I proved something really cool. I proved in the coolest way I've ever seen that the tangent of 15 degrees is 2 minus root 3. And that's a good thing to remember. It's another special angle that you can figure out with all of this. So just as a quick summary, you chase all the lines, AHD and AEB are similar, and that gives you two 15-degree angles.
Yeah. That is
That's
really
probably not
nice.
your
Yeah. That is really a lot of the time, simplest solution, may work for this thing, but it's really we don't learn much. I really like this question, and especially the way you think that, oh, I have a 30, I have a 40, but I like 90. So that's how you draw these to actualize, right? I mean, we learn so much just by, doing different things, and that's what I love about geometries. So thank you for that. It's really nice. I really like it. And lastly, we have the solution using trigonometry over here. Also using, last time we had the formula using the sum of the tangent of the sum, and here's the tangent of the difference, pretty much the same formula, just different side here and here. So you just, again, we leave it for you to review at home if you would like to. But also very beautiful solution. So, I mean, because you got the question very quickly, maybe you can just send us to the chat what solution you used, 1, 2, or 3, or maybe a different one. That would be very good to know. And
Yeah,
then
I am really curious. It was either 1, which is fast if you see the lines, or 3, which is
yeah,
really
I think it's it's 2 has a lot of ingenuities and it takes time. So I would tell that is lesson
2
number.
has not really that much ingenuity, but it does take a lot of time because once you draw the two, yeah, you have to draw the two altitudes. It's just that in the competitions that I do, that's way more common. I draw altitudes all the time. That tends to work. So that's kind of ingrained now.
Into problem solving. Yes. So just looking backward, there's a lot, but really looking at triangles, go through all the special ones, going through similar. A lot of time, actually, we use only congruent triangles with circles, the inscriber, angle theorems, tangents, draw everything. The most important thing is that when you have whatever information written in words there, in the problem, you want to represent it in the picture, right? And then these advanced techniques just require a little bit more practice. But if we know the basic very, very well, right? Like what David's the solution, you know the 90, 30, 60 triangle very well, know a little bit of trigonometry, then most of the time I believe that you can find out the answer to probably the most challenging geometry questions in Math Kangaroo. And as we said earlier, Math Kangaroo doesn't seek to test you complicated formulas or you would have an advantage because you know some theorems ahead of time. Just knows the basic very well and practice, and I think you're going to be doing well. And yeah, one student replied that he used solution number 1. So that's great. That means you are very proficient at drawing actualized. Okay, thank you everyone. So